So we had stopped at this slide where we started discussing about the parallel type configuration for heat exchanger and counter type. So in the parallel type configuration, we have both the streams entering and exiting the heat exchanger from the same end. And the counter type is one stream enters from this side and exits this side. The other stream enters the opposite direction. So the flow is in the counter manner. And we plotted the temperature versus the length of the heat exchanger. So in one case, in the parallel type configuration, the hot stream will cool down in like this, and the cooler stream will get heated up like this. So we see at the end or at the exit of the heat exchanger, the potential for heat transfer is very less. Whereas in case of a counter type heat exchanger, one stream will go like this, the other stream will probably go like this. And we can maintain almost similar amount of potential or both at the inlet and at the exit, or in this case there is no inlet or exit, so at one end of the heat exchanger and the other end of the heat exchanger. So we can maintain more or less constant potential, or the change in potential between one end to the other end need not be as drastic as the parallel type configuration. Okay, and hence in the parallel type configuration, the hot fluid cannot go all the way till the coldest temperature of the cold fluid, and the cold fluid cannot go till the hottest temperature of the hot fluid. Whereas in the counter type, the other one, we can actually maximize the potential of heat transfer. So the cold fluid can probably go till the maximum temperature of the hot fluid, and the hot fluid can come close to the coldest temperature of the cold fluid, and it would be governed by which fluid has the minimum m dot Cp. So whichever fluid has the minimum m dot into Cp, that fluid will undergo the maximum delta T. And in the counterflow arrangement, you can realize the maximum delta T. In the parallel configuration, you will be limited by this phenomena of the two temperatures coming close to each other. So this is where we had stopped. And we also had seen the two configurations, or the configurations are same, but the manner in which these two heat exchangers are made for the liquid to suction heat exchanger. So one is the concentric tube type. So there are two tubes. Consider this as one tube, and the outer one, the annular space, providing the space for another fluid. So one fluid goes through this, the other fluid goes through the annular space in a counterflow manner. Okay, so as I have told, the vapor flow will occur through the larger area, and the liquid flow will happen through the smaller area. Okay, so this is done to minimize the pressure drop in order to make this flow happen. So vapor has lower density, and hence for the same mass flow rate and same length and diameter of the tube, vapor flow will lead to larger pressure drop in case of vapor. Okay, whereas the liquids have lower density, has higher densities, and they will actually lead to lower pressure drop. Okay, so you will have to go back and check the equation for pressure drop across a pipe. So this is the equation. Here V is the velocity. Okay, L is the length of the pipe, and D is the diameter of the pipe. And you convert this equation into m dot, okay, using the continuity, rho into pi d square by 4 into velocity. So you substitute in place of velocity, substitute m dot, and you will see that the delta P then scales as 1 over rho. So any fluid which has higher density will lead to lower pressure drop as long as the length, diameter, and mass flow rates are constant, compared to a fluid which has a lower density. So a lower density will lead to higher pressure drop, and higher density will lead to lower pressure drop. So that's the only reason why we make the liquid flow through a smaller space, or we can allow it to flow through a smaller area when compared to vapor. So that is also true in case of your air conditioning unit. You will see there are two pipes which connect your indoor unit. Okay, one pipe is slightly thinner, the other pipe is slightly bigger in diameter. So the one which is bigger in diameter carries the suction. So that is the suction line to your compressor. It carries the vapor. Okay, whereas the smaller diameter tube which is connected to the evaporator is the indoor unit. Okay, that is the evaporator. So the smaller even diameter tube carries the liquid from the outdoor unit. Okay, you can actually provide the same diameter tubes for both. So that is, you can provide larger diameter for liquid, but that will be more costly. As simple as that. So similarly, in heat exchangers also, we can, let's say I provide 10 millimeter diameter for the vapor side, and I see the pressure drops are negligible in that case. And I can choose to provide the same 10 millimeter diameter for the liquid side also, an effective diameter, okay, effective hydraulic diameter. But then we will see that the heat exchanger is slightly bulky. So you can keep on reducing the size of the heat exchanger from the liquid flow region. Okay, many a times heat exchanger designer choose almost similar pressure drops for both the vapor and the liquid side. So if you provide 10 millimeter on the vapor side and you get some delta P, try to match the same delta P on the liquid side and get the diameter. Okay, so that can be one design point. You can choose a diameter which is bigger than that, but the penalty is more space and slightly more expensive heat exchanger. Okay, the other design was a simple vapor line. Again, you can see the vapor line is significantly larger in diameter compared to the liquid line. So you have these two tubes, vapor line and liquid line. You just wrap the liquid line all around the vapor line. So that becomes a heat exchanger. Only thing is, in this case, you will have lesser contact area, so the heat transfer would be affected. Whereas over here, you have large contact area. Okay. So this is where we had stopped. So in case anyone has any query or doubt. So wherever possible, we prefer counterflow type heat exchangers. Okay, there is another third type of heat exchanger which is called the cross flow, and that is the most common type in air to any fluid heat exchange process. You would see that in such scenarios, wherever air and some other fluid, mainly liquid, I must write, okay, liquid or liquid plus vapor. Okay, so one side you have liquid, the other side you have air. So in such scenarios, air or even any gas, we prefer to have a cross flow type of heat exchanger. Cross flow type is you have one tube like this. Okay, you can have banks of such tubes, maybe two or three, either in series or parallel. So this is the flow direction of the liquid or the liquid plus vapor. Okay, whereas the air or the gas flows perpendicular to it. Now, why this type of heat exchanger is preferred over here is, again, the same logic. If you have to blow air or any gas, you need to provide large diameter ducting in order to reduce the pressure drop. Now, where do you get why do we care about the pressure drop is, If you have large pressure drop, you will have to provide a bigger fan or a blower. Okay, if you have a small pressure drop, a smaller power, a small capacity fan will suffice. So you will see that in such scenarios, you may get diameters of the order of a few hundred millimeter or maybe 20, 30, 40 millimeter as the required diameter. Let's say you get 50 millimeter diameter. Now 50 millimeter diameter pipe to be bent all around this smaller tube would be very difficult to achieve. So what we do is we provide just a duct. So we place this coil inside this duct. This coil takes the liquid or the liquid plus vapor. So liquid plus vapor means your evaporator or condenser. Okay, so your indoor unit and your outdoor unit in an AC, your refrigerators have all the freezer section of your refrigerator. They are all examples of cross flow type. So air will come in from here and it will blow across the coil. Okay, so you will see that heat exchangers are not just designed from the point of view of heat transfer only, but the pressure drop also plays a very important role. So from heat transfer point of view, you may get small diameters, long lengths as the requirement. But in order to pump the fluid, if you require, let's say, 1 kilowatt of power consumption to blow air across the coil, then you will not prefer that when your heat transfer is probably 3 kilowatt. Let's say for heat exchange of 3 kilowatt, you require 1 kilowatt of fan power. Then this is a very poor heat exchanger design. Okay, so a thumb rule is try to keep the blower power or fan power or pump power to less than 5 to 6% of the heat transfer. So if you have a 3 kilowatt heat exchanger, so 3 kilowatt is the heat transfer between the hot and the cold fluid, you will try to keep the power required to blow the fluid or the pumping power for the fluid to around 150 watts, not more than that. So this is kind of a thumb rule. Lower the better. And hence you will see people come up with various types of heat exchanger design. So it is always a trade-off between the heat transfer and the pumping power required or the blowing power required. Anyone knows where the air is sucked in the indoor unit? From which side in your indoor unit of a split AC? So split AC indoor unit just looks like a rectangle or cuboidal box. So from where is the air sucked in?
From the top.
From the top, yes. And the evaporator coil is placed in this configuration. So somewhat like this. It is not vertically placed, it is not horizontally placed, it is placed at a certain angle, around 45 to 60 degree. And if you look at it from this side, it will just look like a triangle. Okay, so it's uh, so the tubes are bent all along this surface. Okay, and then it comes back on the back side and again gets coiled up. And air enters from the top, blows across this triangular arrangement. So it blows across this and then is blown from the bottom into the room. Okay, and the fan itself is placed over here. The fan itself is placed over here. So it sucks in air from the top. And hence the indoor unit should be placed typically around 6 inches below the ceiling. So your indoor unit is an example of a cross flow type heat exchanger. Your outdoor unit is also an example of a cross flow type heat exchanger. In the cross flow type, you do not get the full potential like in a counter flow, but it is again a trade-off between the pumping power required. So in case of air, if you have to obtain the counter flow arrangement, so you will need your evaporator to be in this form. Okay, and then maybe in the annular space, if you have larger diameter in the annular space, you can blow air through that. And this is the evaporator, liquid plus vapor carrying the refrigerant inside. Comes out as superheated vapor or saturated vapor. This would be the arrangement. Okay, so you will see that you require a very long tube. Okay, and lot of fan power would be required in such scenario. So the configuration will not turn out to be a very compact one, but it may be the most efficient one. Okay, so as we are discussing about the heat exchangers, so this would be the right time to discuss about something called the internal and external regime. Okay, so when we are just looking at the thermodynamic cycle of be it a power cycle or a refrigeration cycle, what we discuss is only about the internal regime. Internal regime is nothing but the working fluid. Whereas definitely will be interacting with the external regime. In case of a power cycle, you will have a boiler and a condenser. In case of a refrigeration cycle, you will have an evaporator and a condenser. Okay, so ultimately you will be interacting with two thermal reservoirs, if you remember the terms used in thermodynamics. So if you have a thermodynamic cycle, it will interact with two thermal reservoirs. So what are those reservoirs? Those reservoirs are nothing but the external regime. So in case of a refrigeration system, the external regime on the condenser side is air. Okay, and on the evaporator side is also typically air if you are using it for air conditioning purpose or cold storage or refrigerator. But in case you are using it in a process industry where you have certain food products to be chilled, let's say milk, okay, or if you are uh, using it for breweries, so then you can have, instead of air, you can have some liquid also as the external regime. Okay. Similarly, it need not be always air-cooled condenser. You can also have water-cooled condenser also. So you can have, so most common type of external regimes would be air or water. And your internal regime is the working fluid, which we call as refrigerant. So when we draw the thermodynamic cycles, we always draw the cycles, the state points of the refrigerants. We never care about what is happening to the external regime. Okay, in case of a power plant, we will say that the boiler is operating at a so and so temperature. But that is not the case actually. Your coal is burning at a significantly higher temperature. Okay, so then there will be a large delta T between the flue gases and the water itself, which is boiling. So there is always an interaction between the external and internal regime, okay, through the device called the heat exchanger. And the delta T between these two will also affect the efficiency or power output, or in this case, in case of refrigeration system, power input. Okay, so this will be affecting the overall cycle performance. It is not that only the refrigerant properties is what affects the cycle. we just simply draw the cycle and we don't care what is happening to the external regime. That is not the case. What is or what decides this isobar on the condenser side? Or what decides the evaporator pressure? So what decides this? So the condenser side pressure is decided by the ambient temperature. Okay, and the evaporator pressure is decided by what temperature you are trying to set in your indoor unit or in a refrigerator, whatever the freezer temperature is. So ultimately, it is your requirement which is dictating the evaporator pressure and temperature. So in case of a power plant also, if you change your heat source from coal to let's say LPG, the combustion temperatures will change and hence the external regime will change, which will bring about a change in the internal regime also. Maybe you will see a higher boiler pressure or a lower boiler pressure depending on the temperatures you can achieve, and that will change the power output from the cycle. So when we are looking at the cycle efficiency, cycle throughput, we should always look at both the internal and external regime together. Okay, let's take one example of a Carnot cycle. So this is the TS diagram of Carnot cycle. Just look at this pink cycle. Now this is your condenser. So we are looking at refrigeration cycle, and this is the evaporator. Now what would be the external regime temperatures in this case? Your external regime on the condenser side will be slightly lower. It has to be slightly lower than the condensing temperature, otherwise there won't be any heat transfer. And similarly on the evaporator side, you will have a slightly higher external regime temperature. So consider that your evaporator temperature is 20 degree and your external regime on this side is 25. Similarly, on the condenser side, let's assume that the condensing temperature is 50 and your external regime could be at 45. Some hypothetical numbers I am giving. Okay. So in this manner, can I call this cycle as a Carnot cycle? With this internal and external operating conditions, will this be a Carnot cycle? So if I draw the process diagram for the internal fluid, that is your refrigerant, it looks like a perfect rectangle. Isothermal over here, isothermal over here, isentropic, isentropic. But when I look at the external regime, where the evaporator is cooling a substance which is at around 25 degree, and the condenser is losing heat to a substance which is at around 45 degree. Now with this information, can you actually call this cycle as a Carnot cycle? Do you get my question? Do you guys get my question? Should I repeat?
Sir, repeat one.
Okay. So your refrigerant is undergoing this four processes, which look like a Carnot cycle: isentropic compression, isothermal heat rejection, isentropic expansion, and then isothermal heat absorption. Okay, these are the four processes your refrigerant is undergoing. But what I am telling is during this isothermal heat absorption, the external regime from where it is absorbing heat, it is at around 25 degrees C. And during this isothermal heat rejection, the external regime, the thermal reservoir to which it has to reject heat. You always have these two thermal reservoirs, no? Where the cycle interacts. Okay. So this refrigerant is at 50 degrees C but it is losing heat to a surrounding which is at 45 degrees. So external regime is nothing but your surroundings. So you have two surroundings over here. One surrounding over here, the other surrounding is here. So here it is losing heat, the cycle is losing heat, here the cycle is gaining heat. So now there is a difference of 5 degrees C between the system and the surrounding at both the ends. Now in this configuration, can I call this cycle as a Carnot cycle? The processes are what the Carnot says, isothermal and isentropic. But is it truly a Carnot cycle?
No,
Why do you say so?
because the temperatures of the heat sinks and the process should be same.
Should be same. Very good. So there is some amount of irreversibility over here. It's the heat transfer process. Okay. So ideally, if I have to call this as a Carnot cycle, this 25 and 20 should be same. So it should be either 25 or 20. There cannot be any temperature difference between the external and the internal regime. Internal regime is your system in a simplistic manner. External regime is your surrounding. If I call my refrigeration system as the system itself, thermodynamic system. So everything all around it is surrounding, including the air which it is cooling and the air to which it is losing heat. So, but we know that we have to maintain some small amount of delta T between the two regimes. Otherwise, there won't be any heat transfer. So even if the cycle looks internally very close to a Carnot cycle, yet you will not be able to achieve the Carnot efficiency because ideally with this temperature 45 and 25, my Carnot cycle should have looked like this, a smaller rectangle. But in order to have some finite amount of temperature difference between the internal and external regime, I will have to push this temperature to maybe 5 or 6 degree above 45, and I'll have to keep this temperature 5 or 6 degree lower than 25, or even 1 degree or half a degree. So I can never attain the Carnot efficiency even if the processes internally look like Carnot. Okay, so you can have irreversibilities between the system and surrounding because of heat transfer process. Okay. Now comes another point is, will the external regime behave like a big thermal reservoir? We assume that the external regime is so huge that no matter how much amount of heat you extract or dump to it, the temperature will not change. Hence, we are drawing these horizontal lines. Okay, but let's say you are blowing air over this evaporator coil. So if the evaporator coil has a cooling capacity Q dot, so an air is being blown over it. So MCP of the air into delta T. So this external regime itself will also undergo a finite amount of delta T. It will not remain horizontal. Same goes with the condenser side. So when you're rejecting heat to the ambient, it's not as if the ambient remains at constant temperature. So air, when it passes through the condensing coil, if you just stand in front of that condenser unit, you will see that the air is significantly hot. So eventually these lines which were made horizontal, they will also not be horizontal. They will also have some kind of a slope. So then you will have large temperature differences over here. Okay, so this is the best case scenario. What it says is, let's say my ambient temperature is 25, sorry, on the indoor side, and on the outdoor side, let's say the temperature is 45. It picks up heat from the condenser and it gets heated up, heated up, heated up. Maximum it can go is up to 50 degree. Similarly, on the indoor side, it cools, the air cools, and the minimum it can go is 20 degree. Okay, so these are the two limiting cases. So the process which we were looking at, some parallel processes, they are also not in the same fashion. Even if we consider that the internal regime is undergoing the ideal cycle which we know. Is this clear, or should I repeat again, or some concept is difficult to understand? When can the air temperature, even after gaining large amount of heat or losing large amount of heat, remain isothermal? No change in the temperature at the inlet and at the outlet of the heat exchanger. When can this go to zero? This delta T can go to zero. When? What is the limiting case? When you have Cp tending to infinity. So no matter how much amount of heat you dump, your Cp is infinity. So your fluid will not undergo any change in temperature. Or the other case is m dot tending to infinity. It means that you have such a large fan that it is blowing air at extremely high velocities. And even after it loses heat to the evaporator coil or gains heat from the condenser coil, the temperature change between inlet and outlet is negligible. So these are the two limiting cases when you can have the external regime undergoing insignificant amount of temperature change. But both these cases are both these cases possible or impossible?
Not possible for commercial.
M dot tending to infinity is not possible. How about Cp tending to infinity? Is this possible? I cannot have a fan which blows air at infinite speed, or I cannot have a pump which flows liquid water at infinite velocity. But what about Cp tending to infinity? Cp for air is finite, Cp for liquid water is finite. Is there a case where Cp is infinity? Okay, so think and let me know the answer in next class or in this
During
class.
phase change.
Latent heat.
During phase change, yes. So if and only if the other side, that is the external regime itself, is undergoing phase change, you can expect a horizontal line on the external regime side. But as long as it is undergoing just sensible heat transfer, we will have such lines. Okay.
But sir,
So
in this
yeah,
case, we are already considering it as air or gas.
air or gas, yes. It could be
So
liquid
it's
water,
all
yes.
already in the gaseous phase. So how can we expect a phase change?
Hmm. So, so let's say the evaporator side, you submerge your evaporator coil in a bath of water, which is at 0 degrees C, and you're just making ice out of it. So then your external regime can be considered to be more or less isothermal, just that freezing process. Or if you're losing heat to some other fluid which is undergoing phase change. But these are all extreme scenarios. Most of the time, especially on the external regime, on the condenser side, you will see you're losing heat to the ambient air or maybe ambient water. If you have a large water body nearby, you will, let's say you have a river and you can dump a lot of heat into the water. So you can have a water cooled condenser. Okay. Or you can have a cooling tower just like what we have in Nalanda. We have a big cooling tower. So that cooling tower brings in cold water to the condenser. Condenser gets cooled. Again, the hot water goes to the cooling tower. That is the best that you will see. You will not see phase change happening in the condenser side. But theoretically, CP can be made to the going to infinity on the external side in case you have phase change. And m dot going to infinity is definitely not possible. So most of the time you will see the external regime also undergoes this process line. Now, can you think of a cycle which is definitely not a Carnot cycle, some internal processes which will lead to irreversibility going to zero? Don't think in terms of Carnot cycle, because as you can see, if I have my internal regime undergoing this Carnot cycle, just because of heat transfer processes, there will be irreversibilities. So think of some arbitrary process line which will lead to a perfectly reversible cycle, which will yield me the best COP. Can you intuitively think? You just have to modify these two lines. These two lines are the source of irreversibility. These two horizontal pink lines. My external regime is undergoing this dotted line or dashed line. Okay. So think hard. And I will send you one tutorial, and one of the problem in the tutorial is exactly this. So if you try to superpose a Carnot cycle over this external regime process, you can appreciate that you have large delta T's over here. And this is the source of irreversibility. Now think of a process which will minimize this and make the reversibility go to zero. So modify the internal regime in such a fashion. Okay. So now, yes,
Sir,
someone has answered. Yes.
sir, here already the refrigerant is going phase change. So why do we need the temperature difference
Okay.
between
Why
the
do we need
internal
the
and
temperature
external
difference?
region?
Okay.
Yeah.
Okay. So good that you have asked here itself. I thought that this part was clear. Let's say you have to condense refrigerant at 50 degree. Okay, you have a tube which has vapor at 50 and you want to condense this vapor at this temperature itself. So what would be the process? You will have to bring it in contact with something which is cooler than 50 in order to condense, isn't it? You have vapor. Consider you have steam. Consider you have steam in a container at 100 degree. And now you want to condense this steam. What will you do? If you bring it in contact with, let's say, another fluid which is at 100, will this container having steam at 100 lose heat to this?
No.
Thermodynamically, yes, because in thermodynamics, we think that even for a very small temperature difference, even for delta T tending to zero, I can have heat transfer. So that was the fallacy in thermodynamics. It always dealt with equilibrium processes. But in practice, you will have to have at least a finite amount of temperature difference. So let's say 99 or 98. So what I was telling is around 5 degrees typically what we maintain as a designer. So I will choose to have 95. So then you have a temperature difference between the internal regime and the external regime. So when your air conditioning unit, which is condensing in the outdoor unit at 50 degree, the ambient cannot be at 50. Okay, most of the ACs, they will come with a commercial rating of operating at an outdoor temperature of 52 degrees. Okay, so even if the outdoor air temperature goes to 52 degrees C, your AC will still provide you cooling. It means that your condenser will still be able to condense at 52 degrees C. Does that mean the condenser is operating at 52? No, it is operating at maybe 5 or 10 degree higher than 52. So your condenser is rated to cool your refrigerant vapor even at 60 degrees, 62 degrees, 65 degrees. It depends on how much delta T the designer has chosen. Now is it clear?
Yes, sir. Sir, also in the second TS chart, why is the slope like if we are going from T2 to TC, the left point, the temperature of the external region will increase rather.
So temperature of the external regime is increasing. No? This is the inlet. This is the exit from the condenser. So inlet is at 45. That's what I told. And exit at best can be 50. If this is 50, it cannot go beyond 50. So consider that your vapor is flowing in this fashion and the ambient air is flowing in this fashion. Okay, ambient air enters at 45 degrees C. This refrigerant is entering at 50 degrees C, saturated vapor. It comes out as saturated liquid at 50 degrees C. So it enters as vapor, comes out as liquid. 45 degrees C vapor would have absorbed this heat of condensation, and it is in gaseous phase. So it is sensible heat transfer. So it will undergo some delta T, and the maximum delta T it can come out at is a 5 degree in this case. So it can go up to 50 degree. That is the limiting case. That's what this chart is showing.
Okay.
Any other question? So when you set your AC at 24, so that set point is for air. That is again external regime on the indoor side. So when you set your air temperature at 24, that doesn't mean that the evaporator is at 24. So what you are setting is 24 over here. Okay, let's say indoor air is at 26 or 27. It is entering from the top of the indoor unit, getting cooled and coming out at 24. Okay, so even this condition is not practical. Having delta T over here as 0 is again not practical. So your evaporator in this case may be 2 or 3 degree or even 5 degree lower than 24. So your evaporator could be operating at 19 or even 15 degrees C. So it depends again on how much of area has been provided for heat transfer process. So your requirement is outlet should be 24. In order to maintain the air outlet from the indoor unit at 24, your refrigerant would be boiling at even lower temperature. So that with this delta T, you are able to absorb the heat. So that is what I was telling, that just think if this rectangle is the best process. Because whenever we ask you what is the best cycle possible to obtain the best COP or best efficiency, we always think of Carnot cycle. Carnot cycle is true given that whatever Carnot stated is also true. That is, he always stated that there are two thermal reservoirs, and the definition of a thermal reservoir is it will have MCP tending to infinity. So no matter how much amount of heat you dump into the ambient temperature will not rise. This is what we assumed previously, and the outcome of this is global warming. So even the entire atmosphere is not a thermal reservoir. because it doesn't have an infinite mass, it doesn't have an infinite Cp. Okay, so when you appreciate that nothing can have an infinite MCP, so then from that understanding, then try to modify the process on the internal side such that your irreversibilities in the heat transfer process goes to zero. That's what my question was. So you need not answer it just now. You can think and maybe come up with the answer in the next class. And I told you Carnot cycle is definitely not the answer. Okay. So till now we were looking at a very simple scenario where the internal regime was undergoing the Carnot cycle. Now let's come to the VCRS cycle. Now this is the entire cycle. Now you draw the similar process lines for the external side, which we had drawn in the previous slide. So the external regime in the evaporator side, refrigerant is absorbing heat and the external regime is getting cool. Okay. Now on the condenser side comes the complexity. On the condenser side, once the refrigerant comes out from the compressor, it is in the superheated regime. It is not at saturated vapor condition. So your condenser is eventually partly a desuperheater and partly a condenser. So calling it as a condenser is also a misnomer in one sense. It is not just one process which is happening. It is partially the refrigerant is undergoing sensible heat transfer and the rest is the phase change process. Whereas on the external side, it is still air, let's say, and hence it is just undergoing the sensible heat transfer process. So now in this case, the bottleneck is this kink. So in the previous class, everyone accepted that I cannot have this kind of a heat exchanger where this is the hot fluid and let's say this is the cold fluid. So cold fluid is undergoing this process, hot fluid is undergoing this process. So hot fluid cannot cool below the coldest temperature of cold fluid. And similarly, cold fluid cannot cross the hottest temperature of the hot fluid. So crossing of this process lines is not possible. Okay, and similarly, if I extend that logic to this process also, so if this is the external regime process line, this would be the limiting process line for the internal regime. So at this kink, we have to observe there should not be any crossing of the process line. So it cannot be, the external regime cannot go like this. Okay, it cannot cross here and here. Okay, so you can have the external regime going like this, can be well below this line, but it cannot cross this. So when the condenser is designed, we take care of this. Okay, because such physical processes are not possible in the field. Now, what decides the slope of this line? Or in the previous case, what is deciding factor for the slope of this line?
M dot Cp.
M dot Cp. So as a designer, I have no control over the Cp. Cp of air is fixed. So as far as the design is concerned, I have only m dot to play around. So if I increase this m dot, the slope becomes flatter. If I decrease the m dot, the slope becomes steeper. Okay. So when I have to design the condenser, so I have to properly decide about the m dot air. That means I have to properly size the fan because fan is what decides the m dot. Okay, so that If I want my condenser to operate, let's say at 55 degrees C, when the ambient is at 40 degrees C, so I have to ensure that this process line, these two process lines ensure that at this point you still have some finite amount of delta T. Okay, so this is the extreme case where this point, okay, this point has a technical name. This point is called the pinch point. So pinch point in a heat exchanger is that point where you have minimum delta T between the hot and the cold fluid. Okay, in this case, that point could be here. In the previous case, the pinch point was at this point and at this point. So ideally, you can design a heat exchanger with a pinch point delta T of 0. That is the ideal case. But practically, when we design, we maintain around 2 to 3 degrees C headroom over here. So I will not be designing the heat exchanger for this kind of a process. I will probably push my design. So I will have a slightly higher condensing pressure to maintain some finite delta T at the pinch point. Okay. Now, as soon as I shift from this point to this point, now you can appreciate, now this is my line for which I will design. You can see now the cycle refrigeration effect has reduced. It has now become only this much. Because I had to maintain a finite amount of temperature at the pinch point, I could not follow this ideal line. I had to push my condensing pressure. So your compressor will also have to compress more. You obtain a less amount of refrigeration effect. Okay, and that's why we try to subcool also, so that whatever we are losing now here, we try to gain it back. So if I ask you what decides the condensing pressure, it is decided by the heat exchanger. If I have a very compact heat exchanger, I will see that I will require large delta T's across the internal and external regime. If I have a huge heat exchanger, I can work with delta T going to 0. So hence a 5-star AC will have a larger heat exchanger both in the indoor side and on the outdoor side, because a larger heat transfer area ensures that I can have the same amount of heat transfer across a smaller delta T. Q equals to H A delta T. I give in one case 1 meter square area, in another case 1.5 meter square area. So in this case 1.5 meter square area, I can have a smaller delta T for same amount of Q dot. Okay. Now, what is the benefit of smaller delta T across the internal and external regime is I minimize the overpressure required in the compressor. So in this is the ideal case where delta T is 0 at the pinch point. I would like to operate at this point, but practically I'll have to maintain 2 to 3 degrees. Let's say someone comes with a cheaper AC. So cheaper AC means all the materials used either have to be of cheap quality. So instead of copper, you may be using aluminum. That is one thing that many manufacturers do. Let's say the material is same. So then you will have to cut down on the heat transfer area, assuming that the compressors available for both the cases is same. So let's say I give two compressors of same manufacturer to two suppliers and ask them, one of them makes a cheaper AC, the other one makes a slightly more expensive AC. Okay, the cheaper AC will use smaller heat transfer areas in the indoor and the outdoor unit. What is the repercussion? Compressors are same for both. The repercussion is even if the compressors are same, they will not be seeing the same pressure ratio. One, because it has a smaller heat transfer area will be operating at a higher condensing pressure, because it will require larger delta T to have the same amount of heat transfer. So one would be probably operating here. The other, which is a larger heat transfer area, would be operating at a lower pressure. Same goes over here also. Here the pinch point is this. Definitely you cannot work with a pinch point delta T equals to 0. So you will have to pull down the evaporator temperature. So you cannot work with this evaporator temperature, you will have to work with this. So in one case you might be operating here, the other one could be operating here. So let's draw the two cycles with different colors. So the larger heat transfer area, the cycle will look like this. Whereas for the smaller heat transfer area, the cycle will be the red one, like this. So your heat exchanger size also determines the temperature at which you can condense, and hence it determines the pressure at which your condenser is operating. Similarly, on the evaporator side, it determines the temperature of the evaporator, and hence it determines the pressure of the evaporator also. And now once the pressure of the evaporator and condenser are set, then that is the pressure ratio that the compressor will see. So if you just take out the compressor from a 3-star AC and you connect it to larger heat exchangers, the same compressor would be consuming lesser amount of work. So we always think that the innovation of a 5-star AC vis-a-vis a 3-star AC is only the compressor. That is not the case. The extra money that you pay is both on the compressor, spent on the compressor, as well as on the heat exchanger area. Questions?
Sir, the isotropic line will also move towards the right, 1 to 2.
Oh, sorry. Yeah. Thank you for pointing it out. Yeah, it would be helpful. Yeah, thank you. Anything else? Okay. So these two slides just tell you whatever I have told you. That pinch point is a very important thing to consider in any heat exchanger design, and it has practical implications in our refrigeration cycle. Okay, so this is the ideal case for your condenser side. This is what we will actually design it for. So we maintain some amount of delta T, which is of course not 0, for our heat exchanger to operate. Okay. Which type of heat exchanger I have assumed in all this analysis? Which type of heat exchanger? Parallel, counter, cross.
Counter.
Counter.
So this is the best case scenario still, huh? And now think of the actual heat exchangers which we have. They are not even counter, they are cross. Okay, so they work with much larger delta T's. Okay, so the next slide is just a slide which reminds you of this Moody's diagram, which you would have seen in your fluid mechanics. Okay, so you would have studied minor losses, major losses, or you would have heard this term head loss or something of that sort. So minor head, major head. Different books have different terminologies. The whole idea is even in a straight pipe, because of viscosity, you have pressure drops, and hence even if you have to pump water in a horizontal pipe, you require a pump, an external work input device, to overcome this pressure drop. Okay, the viscosity information is provided in this friction factor. So friction factor for laminar flow is 64 by Re, which is shown over here in this chart. And then in the transition regime, in the turbulent regime, we have these separate lines. The pipe roughness plays a role. Okay, because Reynolds number is an important factor, and friction factor is what this chart gives. So this slide is just to remind you that whenever you have flow in a pipe, you will always have some pressure losses. Okay, and larger diameter pipe will lead to smaller pressure loss. Okay, so this you would have studied as a part of the major loss. And in minor losses, you would have studied about the bends, area changes. So if you have a sudden contraction or a sudden expansion, or if you have a sudden change in the flow direction, or even if you have a 90-degree elbow like this, if you have a valve. So all these things also lead to losses, and their loss coefficient was provided in a handbook in form of K factor. I hope you would have studied these things in fluid mechanics, no? Second year. Don't remember? Remember seeing this diagram?
Yes, sir.
So this was not taught to you just for the sake of teaching. So it has again field application. So if you have to decide about the pipeline diameter, if you have to size the pump for your home, you will have to go through these pressure drop calculations. Otherwise, you cannot size the pipeline diameter or the pump. So till now, whatever cycle we have studied, the VCRS cycles, they were all standard cycles. So another name for the same cycle is standard saturated single stage cycle. So standard cycle means no pressure drops in the refrigerant pipeline. Okay, so we were assuming it to be isobaric. Saturated means in the system without any subcooling or superheating, we assume saturated vapor over here and saturated liquid over here. Okay, and single stage means we are compressing the vapor in a single stage compressor. We are not multi-staging it. We are not compressing in one compressor and then sending it to another compressor and recompressing to achieve higher pressure. So whatever cycle we have studied till now, another name for that cycle is standard saturated single stage refrigeration cycle. Okay, so if we look at the actual cycle will significantly deviate from this standard assumptions that we have made. Okay, one is you will have frictional pressure drops in the pipelines. In case you have an LSHX also, you will have some pressure drops in that heat exchanger also. Okay, definitely we will have some amount of subcooling, some amount of superheating if you have LSHX. Even if you don't have, there is a chance of the manufacturer designing the evaporator to have some amount of superheat at the exit of the evaporator just to ensure that there is no liquid entry to the compressor. So then again, saturated assumption goes out of the picture. Standard assumption is not there because you will have some frictional pressure drops. As I showed you, if in case you have access to the ACs for students who are still at home, you can just open the plastic cabinet of your indoor unit and you will see that huge number of tubes are present, either in this fashion or in this fashion in the indoor unit. Similarly, you will have huge number of tube bends provided in the outdoor unit. So each straight length will have some frictional drop. Each bend will also incur some frictional drop. And they are, if you actually straighten them out, they'll run into few tens of meters. They are closely packed in a very compact fashion. But if you straighten them out, they'll be running into few tens of meters. So your refrigerant is actually flowing through those long tubes, both in the indoor unit and the outdoor unit. So you will definitely have significant pressure drops in the refrigerant line. Then we will also have pressure drops in the valves of the compressor. So as you come for the lab class, you will see that the suction line, the discharge line, they have valves, okay, and they require some pressure drop to be to operate. Okay, so you will have to lift a valve, even if it is a small plate like a assembly. So if you have to lift this valve to come out of this chamber, it will require some amount of finite pressure drop across this valve itself. So you will have some pressure drops even in the suction and the discharge valves of the compressor. Okay, and then definitely your compressor is not an isentropic device, so it will have isentropic efficiency which is less than 1. Okay, if you have any connecting pipeline, it all comes under this first category itself. You can also have pressure drops due to hydrostatic head. Now, what is this? Your indoor unit and the outdoor unit are not placed at the same height. That is a possibility. Or in your refrigerator, you see the freezer is on top, whereas the compressor is placed at the bottom. So compressor is also pumping the fluid all the way till the top. Okay, so you also have the hydrostatic heads coming into picture. Okay, and then again, this students who will come to lab, they will see that we always place a filter in the line. So even there is pressure drop across the filters. We also have a dryer just to absorb any moisture in case while filling the refrigerant, there is some entry of air along with moisture. Just to capture that moisture also, we have filter come dryer. So you will have, this is again very small amount of pressure drop, but the everything plays a role, which we don't consider when we discuss about the ideal thermodynamic cycle, standard saturated single stage systems. Okay, we'll not be discussing about multi-stage in this class, but when there is large temperature difference between the evaporator and the condenser, we go for multi-staging. We will see in the compressor discussion that how to identify when to go for multi-staging. Okay, so that we will see, but we will not discuss the nitty-gritties of the multi-stage cycles. Okay, and again, people who will come to lab will see that you have heat transfer also in the compressor. So compressor assembly has both the compressor and the motor together, and they need to be cooled. We assume it to be an adiabatic device and all those things, but you have heat transfer. You have to cool the motor winding, and the compressor itself, it loses heat both to the ambient. Okay, there are open type compressors which lose heat to the ambient, and in case of a hermetically sealed compressor, everything, the entire heat transfer is taken up by the refrigerant itself. So there are so many assumptions which we make while drawing the cycle, which are not actually relevant in the actual system. So these are just the cycles. These are all qualitative cycles. They are not to be quantified. So this is how probably your cycle will look like when you take into account all these non-idealities which we have discussed. So your evaporator will not work in an isobaric fashion, though we assumed it to be an isobaric process. So there will be pressure drop. So your inlet to the evaporator will be at a higher pressure, outlet will be at a lower pressure. This is not to scale, okay? Then this is what you achieve. Then eventually you may have some amount of superheating at the in the evaporator itself, okay? Useful superheating. Okay, so this is denoted by this. Then as the connecting pipeline goes to the outdoor unit, in case of a split AC, you may have some useless superheat. So this line shows the useless superheat. Then when it enters, when the vapor enters into the compressor chamber, so this is your positive displacement compressor, reciprocating type. So you have two valves. So this valve has to be pushed down in order for the vapor to enter. So in pushing down this valve also, the vapor has to do some work, and that will lead to some pressure drop across it. So any valve is a throttling device. So it will have to push this valve down. Okay, so the pressure at this point and this point will not be same. So this is that process line. Okay, there can be in the pressure drop in the suction line and pressure drop across the valve. So these are just qualitative things. Okay, the process exactly need not look like this. This is how we envisage the system may look like. Then what we assumed was something of an isentropic process during the compression process. Okay, definitely will not reach this isentropic point. You will reach somewhere on the right hand side, and the process itself need not follow the particular path that we draw, something of that dotted line. It can follow any arbitrary path, because in this process there is also heat transfer. Okay, so this line itself is again just an arbitrary line, just to show that we don't know the process actually. And then this is, let's say, the exit or the discharge from the compressor. Again, when it comes out of this compressor, it has to push the valve up and then come off. So there will be some pressure drop as it flows across it. Again, there is a pipeline connecting all the way. There is also a muffler placed. In case of a reciprocating compressor, we have to reduce the noise. So there is a muffler also placed at the exit, just like your IC engines have. So it is like a silencer. So it has to pass through that also. So once it goes through that, it will undergo another pressure drop. And then it reaches the condenser. And again in the condenser, even though here it is not shown properly, in the condenser also you may have some pressure drop like this. Okay, so it is written here, but it is not evident in the photograph. So from 2B to 3, you may have some pressure drop. And then you can have some amount of subcooling. Okay, and then you can have the expansion process. So there is written as heat gain in the liquid line. Okay, so this could be a useless heat gain. Before the expansion, there is a possibility of the liquid line not being properly insulated and it gains heat. So there are so many sources of non-idealities, and if we just start counting them and try to draw the cycle itself doesn't look familiar at all. Okay, any questions? So this is where we will stop our discussion on the VCRS cycles. And now we will move on to the gas cycles. So in gas cycles, we'll just touch upon the reverse Brayton cycle and the reverse Stirling cycle and look at their applications. And then we'll again come back to the VCRS cycles discussion when we discuss about the compressors, the expansion device. Okay. So our main focus in this entire syllabus is going to be VCRS. But that doesn't mean that we should not learn about the cycle which is operating in an airplane. That is not a VCRS cycle. Or the cycle that we use in ships to carry liquefied natural gas. So we'll just touch upon those cycles. We'll briefly understand that what is the application, and then we'll come back to the VCRS cycles. So in case you have any doubts related to the VCRS the cycles, the processes that we have discussed. I will send one tutorial today itself, which will help you to understand what types of questions are expected and whatever we have discussed now you will be able to apply it to solve certain problems. So in the gas cycles, as I told you, we will look at two cycles, the reverse Brayton and the reverse Stirling cycle. So anyone remembers the Brayton cycle? What are the processes? Don't remember, then you don't have to think too much. What we have discussed in VCRS is still true, more or less, in case of a Brayton cycle. So in a VCRS cycle, these are the two isobars. Isobar, isobar. This is isentropic. And this was supposed to be isentropic, but we made it isenthalpic, saying that since it is this expansion, this isentropic expansion is occurring very close to the liquid region, the amount of work output that I will get over here would be a very small fraction of the work input. So we actually modified it from isentropic to isenthalpic by replacing that isentropic expansion device with an isenthalpic expansion device, which is nothing but a throttle. Okay, so these were the four devices or four process lines. So throttling process, isobaric heat absorption, isentropic compression, isobaric heat rejection. In Brayton cycle, it is just shifting of this entire process to this region, far away from the dome. Okay, so instead of seeing this as throttling process, you go back to the isentropic expansion process. So this would have been the process. Problem with the So how will this same process look like if I shift the entire cycle to the superheated region? It will look like this. Somewhat like this. Okay, so these are the isobars. This is the isentropic line, this is the isentropic line. Okay, so the process lines for VCRS and a reverse Brayton cycle are more or less same. One is operating in the two-phase region. The other one is simply operating in the superheated vapor region. No phase change at all. So where I get the refrigeration effect is this. What is the total work input is this. All the concepts that we have learned is still the same. Okay. And now in this case, since both are in the vapor region itself, we do not replace this isentropic expansion process with an isenthalpic throttling process. Okay. So we still maintain the turbine that is supposed to generate the power. The logic remains that now in this case, the amount of power generated here would be a significant fraction of the amount that we have to provide in the compressor. Okay, it could be of the order of 30 to 40%. Whereas in this case, first of all, getting an expansion process within the two-phase region is impossible. So we'll have to subcool and then expand. And then we will see that this is probably giving us 3 to 5% at best. Whereas in this case, we can gain 30 to 40% of the power from here itself. So we do not remove this turbine. We keep it as it is. So this is the idea behind the reverse Brayton cycle. Rest of the processes are same. Isobaric heat absorption, isobaric heat rejection, isentropic compression, isentropic expansion. Now, I will not go into the details of deriving what is the COP of this. These things you should have done in your thermodynamics class. And what is the typical working fluid? Air or any gas. It could be any gas which is not undergoing phase change for the operating conditions. So this derivation, you can have a look at it later. So that is not the most important aspect in our discussion. Okay, so this just shaded line shows you the comparison of a Carnot cycle and the reverse Brayton cycle. So this is how the Carnot cycle would have looked at like operating between this T1 and T3. Okay, so T3 being the ambient temperature and T1 being the temperature that you maintain in your refrigerated space. Okay, so refrigerated space. So let's say you want to cool the air till T1. Okay, so this in an ideal Carnot cycle, you could have maintained a rectangular process line like this: isentropic, isothermal, isentropic, isothermal, and this would be the entire cycle. It would have looked very small. And definitely the COP of that reverse Carnot cycle is going to be significantly higher than the COP of this reverse Brayton cycle, because reverse Brayton cycle will have this much amount of work and only this much amount of refrigeration effect. So smaller refrigeration effect, larger working. You can look at it from the area point of view, you can look at it from the mathematical expression. You will get the same thing. So where this is used is in your aircraft air conditioning. Just a small introduction to the cycle on which your jet engines operate. Okay, so they are actually an open system or open cycle. So you take in air from the ambient, you compress it, okay, you provide heat. So your air is the working fluid. If you were to look at it as a standard air cycle, so you have air coming into this compressor at the ambient condition. The ambient in case of jet engines when they are flying at cruising altitude, any idea? What is the ambient pressure and temperature? When the planes are flying at the cruising altitude of, any idea what is the cruising altitude? How tall is Mount Everest?
8 kilometer, 500 meters.
So now just try to guess what would be the cruising altitude of planes.
10,000 meters.
Yes, good. So that's quite close. Yes. Okay, so most of the modern jet planes, they can cruise at that height. Okay, so what would be the pressure temperature? Anybody? Nowadays, even the planes, they have that display, no, where they show what is the outside temperature and pressure. Some of uh, the premium airlines. Has anyone bothered to observe? People living in mountains, they should be able to answer. People who trek, what would be the pressure, temperature? No engineering guesses.
Minus 20 degrees Celsius.
Anybody else? And pressure? Anyone from the uh, states of Himachal Pradesh, Uttarakhand? Anyone from Sikkim? Nobody from there? So typically the outside temperature would be of the order of minus 40, minus 45 degrees C. Okay, and the pressures could be as low as 0.4 bar. Okay. So what we have to first do is compress this air. Okay, we compress this air and then we add heat. So adding heat is just to combust some fuel. What is the fuel? What is the fuel in your jet engines? Petrol, diesel? You don't know the fuel used in jet engines. Come on, this you should find it out. Okay.
So
Yes.
was it some hydrazine plus oxygen?
Hydrogen. I'm not
Hydrazine.
talking
Hydrazine.
hydrazine. What is this hydrazine?
So, so it was a nitrogen compound. I'm not accurately sure.
So are we talking about jet engines or rocket engines?
Sorry, sir.
देखा होगा यार, टैंकर आता है प्लेन में फ्यूल भरने. Never bother to look on that tanker what is written. Next time you should see.
ये केरोसिन.
केरोसिन, हाँ. वही वाला जो राशन में मिलता है या कुछ अलग
नहीं
है?
नहीं, ये प्योर होता है.
प्योर होता है. So that is called aviation grade kerosene. So you would have smelled that also. Sometimes when the engine just starts, you can smell it. Sometimes the fumes go into the air conditioning unit, and through the air conditioning it enters the fuselage. So kerosene plus air is burnt, and then you expand the gases through this turbine, and then you pass it through this nozzle. So whatever the potential is after combustion, do we get that entire potential or extract that entire enthalpy in form of the turbine work output in the jet engine? So where do we get the thrust in the turbine or something else? So we get the thrust by pushing out this hot accelerated gases through this nozzle. So there we get the thrust. So this turbine is just to run the compressor. So if you look at the cycle, so in the reverse cycle, the reverse Brayton cycle, this would be the directions. So what I was telling is you will get around 30 to 40% of the work in this turbine, and which you can feed it to this compressor. Okay, if I reverse this, I get the Brayton cycle. This is the power cycle. Now in this case, this is the compressor and this is the turbine. Okay, so here I will only need 30 to 40% of the work produced here to operate the compressor. So rest 50 to 60% is the thrust. So I do not expand it completely in the turbine. I do not extract all the potential. I expand it only till this point so that I can run my compressor. The rest is passed through the nozzle. So I still have this much potential. Okay, I increase the speed of the gases, convert the static enthalpy to kinetic energy, and then release it from the back. Okay, so if I would have extracted the entire potential, I will give 30 to 40% to the compressor. What will I do with the rest 50-60%? So if I have to create a power plant out of this, then so if this engine is operating on the ground, I want to generate power from this cycle, then I will extract the entire energy which is available after the combustion and pass it through this turbine, expand it as much as possible, get all the work output 30 to 40% will go into running the compressor, rest 50 to 60% is what I get, or whatever corresponds to this area. Okay, and that from there I can run a generator. Whereas when you're flying, you don't want to extract all the work in the turbine. Your major or your main aim is to fly the plane. So majority of the energy has to be extracted in form of thrust. So that's why we have lesser number of stages here in the turbine. Now, since we are compressing the air and then burning fuel into it, okay, so what we do is, even in case of a reverse Brayton cycle, when we have to run my refrigeration cycle, I still need a compressor. Okay, I can borrow this compressor or I can bleed some air from this compressor and then run it across the other processes and get my refrigeration. That is the idea behind using air as the working fluid in case of a jet engine, because you already have the compressor there, okay, which is compressing huge amount of air. So you can bleed some amount of air from there and operate your air conditioning cycle. Okay, in the olden days when we didn't have the jet engines, okay, it was very difficult to provide air conditioning because we had to resort to the VCRS systems only. And flying this entire VCRS system along with the plane. Your VCRS system is using refrigerant. It has its own compressor, evaporator, and condenser and everything. Okay, whereas here you can borrow the engine's compressor, okay, and then extract air from there and use air as the working fluid itself. You don't require heat exchangers now. Okay, because there is no secondary fluid now. Your air itself is the working fluid, and once you cool the air, you don't even need this. You don't even need this process line to close. You get the cold air and directly blow it into your cabin. Lesser number of devices, better it is for systems which are in motion. Okay, so that's the idea behind using the reverse Brayton cycle and not the VCRS cycle, because you will have to carry the entire refrigerant pipeline, condenser, evaporator, everything. You will require heat exchangers there. It is going to be a closed cycle, your VCRS cycle. Here you can, now since air is the working fluid, you can just use it like an open cycle. So now that we know what is the ambient pressure and temperature, can you tell me what are the functions of the air conditioning unit in an aircraft other than cooling? The name is given over here. The air conditioning unit in an aircraft is also called the PAC, pressurization air conditioning kit. Okay, so you cannot breathe in 0.4 bar, 0.5 bar without feeling sick. So the ability to fly our commercial airlines at such altitude without the inhabitants feeling sick. Okay, so this ability has been provided because we are actually pressurizing the outdoor air and then cooling it and sending it into the cabin. And that's why if the air conditioning unit fails, the pilot has to immediately land the plane. So normally with one air conditioning kit, he can fly the plane at a lower altitude. If both the units fail, definitely he has to land. The regulation is if both the unit fails, you have to immediately drop in that oxygen mask, and the first the attempt that the pilot has to make is to come down to 8 to 9,000 feet. So which is around what 2.5 kilometers, 8,000 feet. Any hill station at 8,000 feet? I think Gangtok is at 6,500. So somewhere close to that level. So that we are safe. So the most important aspect of the aircraft air conditioning system is actually the pressurization. So you can imagine your aircraft body to be a pressurized balloon. Okay, it is pressurized continuously by your air conditioning unit. So continuously, some pressurized air is being filled into it. And then there is a tiny valve at the back, which is releasing at a controlled rate this pressurized air. Okay, so if we continuously just pressurize the cabin without releasing the air, so then it becomes a balloon which can burst. So it is continuously being pressurized and it gets depressurized. Of course, there are leaks in the doors and everything. So there are certain leaks there also. But there is a relief valve at the backside of the plane near the tail, which releases. So we are breathing in and exhaling carbon dioxide. So that air has to be released out. We cannot continuously recirculate the air inside. Okay, so along with that, we are so this release is provided not only just for the ventilation purpose, but also this continuously pressurized air. We have to maintain a constant pressure. Typically, 0.8 to 0.9 bar is what is maintained, not 1 bar. Okay. But then the question is, if the outside is at minus 45 degree, why do we need cooling at all? So what is the source of heat in your plane? What is the source of heat?
Combustion of gases.
Combustion of gases is happening in the engine. It is not happening in the cabin. And have you seen the engine in thermal contact with the cabin? It is on the wings. And if there was a thermal contact with the cabin and the engine, we couldn't have survived. What is the typical speed at which these aircrafts fly? Achha, even if we don't consider that, one is an obvious source of heat. What is that? What is the source of heat in your home or in a car when you have all your windows closed? You just keep your car outside for a while.
Sun.
Yes, solar radiation. That is one source. The other source is the skin friction, the drag force. Okay, so at such speeds, there is lot of heating on the skin panel of the aircraft. Okay, and we human beings are also the source. Okay, if you keep 180 passengers in such a small space, try it in a big hall without air conditioning system. You know what will happen. Okay, so these are the three major sources, and then you can have some electronics which needs to be cooled. Okay, those are all secondary sources which are not as significant as these three. Solar radiation, the frictional, skin friction, okay, and the human beings themselves. Okay, so let's look at the process. So as I told you, the compression in the engine, it happens in multiple stages. So we have a LP and an HP stage. So low pressure compressor and high pressure compressor. Okay. So we take or bleed air in between these two stages. Okay, so let's look at the process lines. So already, let's say this is the ambient air. Ambient air is at -40, and let's come up my zero point 0.4 bar, or let's say 0.3 bar. That is the ambient air. It gets compressed. Okay, for the time being, let's assume at around 1.5 bar. The temperatures at the exit would be significantly higher after this compression process. Okay, so this air is then bled, and then we first cool. We cool this air in a heat exchanger. Now, in order to cool this air, we again use the ambient air which is available. Okay, and that air is taken in from the bottom side of the fuselage. Okay, there are two inlets provided here in order to cool this pressurized hot air coming from the compressor. So this air is being bled to the air conditioning kit, which is a small amount compared to the amount of air which is going into your combustion chamber after the high pressure compressor. Okay. So now this air, after it gets cooled by again the ambient air itself, so assume that this air inlet passes through this heat exchanger, and my hot and pressurized air is now cooled. Then it passes to another compressor. Now this compressor is not part of the engine. This is a secondary compressor. So if I look at the process, I cool and then again compress. Why didn't I cool the hot gases from here itself? Why did I pass it through the primary heat exchanger? When my aim was to compress it to a higher stage or higher pressure, why did I cool it and then compress? Please remember the concepts which I have taught you already. Work of compression is VdP. Okay, V being the specific volume, or you can see it as dP over rho. Now, if I cool the gas, I can increase its density, and hence in the next stage now, my compression work will be lower than if I had done the compression process straight away. So whenever we have multi-staging, you will see, and if we want to reduce the work of compression, we place some kind of a heat exchanger between these two stages. Okay, so we cool this air and then compress. and then compress it to a higher pressure. Okay, and then again cool. This is the second heat exchanger, and then expand it. So this was at 0.3 bar. Now, these are some typical numbers which I am choosing. This could be to around 2 bar, and then this is 1 bar or 0.9 bar. So this is your cabin pressure which you want to maintain. So you expand it after this secondary heat exchanger. And whatever work you get from this, you use it for this compressor. So these two are on a single shaft. And now this air is directly fed into the cabin. There are other control units which I am not discussing. So we are just looking at the cycles. Okay, the temperature at the exit may be suitable for cabin cooling, but the humidity and all may not be suitable. So there are other processes in which we control the humidity. So right now we are not looking at that humidity control part. Okay, so this is the major components of the air conditioning kit in your aircraft. So questions or any part of the process which you didn't understand? So remember, whenever you want to compress, you would like to shift the compression process towards the left. Okay, and whenever you try to expand, you would like to shift the expansion process towards the right. In a power cycle, you would want your turbines to be working on the right hand side and your compressors to be working on the left hand side. Okay, so any query in the process itself? So I will repeat very quickly. You bleed some air from the engine compressor itself. Okay, so this is the air which is being bled from the engine compressor. You cool it, then compress it, then again cool it, and then expand it. And the expansion work is fed into the compression work. So this compressor is being driven by this particular turbine. So it may not look exactly like a single stage reverse Brayton cycle, but the processes are taken from the reverse Brayton cycle. Okay, and the air required for cooling in these two heat exchangers is also from the ambient, and we have these two inlet ports. So they are called ram air inlet. The air gets rammed into a smaller area. So this combined unit is called the air cycle machine. And this is the entire air conditioning kit. So you have two such kits near the wings of both the sides. Okay, this portion is the air cycle machine. You can see some volute casing over there. Let me expand this. Okay, so these are the heat exchangers. And this is the compressor and turbine unit. There are other systems also in place in order to control the temperature and humidity, so which we'll not discuss in details in this class. Okay, any questions? We have just 1 or 2 minutes left. Okay, so this is the entire process. So right from the air which enters this engine, so this is part of the engine itself. So this compression is part of the engine. From here onwards, it is happening in the pack, this portion. We cool, compress, again cool, and then expand. Your P6 is your cabin pressure. Okay, and when the aircraft is on ground, then how do we provide the air conditioning? We have to provide it through an external system. This system is the VCRS system. So when the aircraft is on ground and the engine is not running, we supply the cold air from the outside system. That is a VCRS system, just like your air conditioning, residential air conditioning system. And this is operated typically by a diesel generator, or could be a diesel engine. So when the engine is turned off, your air conditioning stops. Okay. One thing which I missed probably is the outflow valve. So as I was telling, there is an outflow valve. So this is the outflow valve. It operates intermittently to maintain the cabin pressure at a steady value. So as it allows the air to go out, it releases all the carbon dioxide rich air to the ambient. Questions? No? No questions?